So I think I forgot to send out a message. These are up, but I didn't tell you guys they were up, so that was my bad. Okay, introduction to linear graphs. So now we're at chapter 2, which is the linear graph models chapter. So in chapter 2, we're going to construct a new type of model for our systems. We've seen schematics for electrical systems. We've seen schematics for mechanical systems, pretty basic schematics, but just, like a mass and a spring, and that type of thing. And we've seen for electronic systems how to come up with a mathematical model using a differential equation for these systems, but we haven't yet talked about what's going to be the sort of central modeling technique for this course and then the system dynamics course, which is called linear graphs. Engineers often use graphical techniques to aid in analysis and design, as we've seen extensively. Often we will write some sort of graph or some sort of graphical depiction of a system without even thinking what we're doing. We're just start drawing stuff, right? And it's effective that way too. But sometimes we get a little bit more intentional about it. Sometimes we align our chi and step into the blessedness of the everyday. I already know the jargon, I feel like. I think I could make this work. Okay, so we're engineers, so let's learn a new one. We will use linear graphs to represent the topology or structure of a system modeled as interconnected lumped elements. So it's going to be a little bit like a circuit diagram, which also represented the structure or topology of the interconnection among lumped elements. But it's going to be a little bit different. We'll talk about the analogy. First, this represents to us the essential structure of the system in a minimalist form. In this way, it is like Massimo Vignelli's famous 1972 New York subway system map, which inspired widespread adoption of his style, as in figure 2.1, which is this is actually a modern sort of reproduction. It's not Vignelli himself. This is actually from present day New York subway. But this is the style that he created, and his original ones look very similar to this. Notice that these subway tunnels, they don't actually run like this. Like they're very straight lined, and then they have these sharp turns and stuff. There's nothing like that in real life. However, it does roughly locate the stations where they physically locate. They're not perfectly right there on the map. If you were to look at the coordinates on the map, it would be a little off, but they're close, okay, to where they are in laid out in the map. So if you know you are wanting to get to East Village, you know that your stop's going to be Astor Place. Like you can tell that from the map. And if you knew where streets were in East Village, you would probably know the Astor Place. I believe it's a street there, and it would be roughly here. But the idea of this is you don't really care exactly how the tunnel runs or exactly where these things are located. What you care about is how to decide which train to get on and which direction so you can get from one place to another place. So if you're like, I want to get from East Village over to Chelsea, then you're going to have to hop on something that gets you down to the red line over to the blue line and then up. And that's how you map out how you want to get from one place to another place. And that was greatly simplified with this. Otherwise, it looks like a spaghetti bowl. And it's really hard to decide how you're going to get from one place to another place. So it's pretty cool. And so actually people hated it when it first came out, but it's almost universally been adopted for this stuff, even internationally. So Paris's essentially subway system has, when I was in Paris, I was like, oh, it looks like a Vignelli map. It's cool. So anyways, this style is neat, but we can learn from it. Not just that minimalism is great, but sort of the key idea of his subway maps is that the details of the tunnel's paths are irrelevant and in fact distracting to the person attempting to get from one station to another. And so he distilled it down to like the bare essentials of what you need from the map. In a similar way, a linear graph represents the system in a minimalist style, with only two types of objects in them. So one of them is a branch, so the linear graph is made up of a set of branches, each of which represents an energy port associated with a system element. Each branch is drawn as an oriented line segment, so it's drawn as a line with an arrow in the middle of it, typically. And so these branches represent for us different one-port elements. So could be a resistor, could be a capacitor, an inductor, could be a source, could be a mass or a spring or a damper. Any of these things could be represented by a branch. And also, the other thing that's in there are nodes. So each node represents a point of interconnection among system elements and is drawn as a dot, like that. So the form of the dot doesn't really matter. It can be an open dot, it can be a closed dot, either one's valid. But the idea with these nodes is that they represent where branches interconnect to each other. So if a resistor connects to an inductor, then they connect at a node. Okay? All branches begin and end at nodes. The nodes represent locations in the system where distinct across variable values may be measured, which is an important point. For instance, in a circuit, wires are where we would measure the voltage, right? And those wires represent nodes. We've talked about them as nodes before. We've called them nodes. We'll actually expand on that example of the electronic circuit in a moment, and we'll talk about how wires are nodes. But let's look at just a branch that begins and ends at nodes. So a branch always begins at a node and ends at a node. And it has a through variable that goes through it, which if a generalized version is f, but if we had for instance, a specific energy domain, so for instance, if it was a spring, what would this through variable be? What's the mechanical translational through variable? Force, right? So it would be force. The force flows through the spring. And the two nodes represent the two ends of the spring, okay? And each one would have a velocity, or just a generalized across variable. It could be a voltage, if it's a circuit element, or whatever. So V1 minus V2 is the across variable for this element, for this branch. And an across variable always has somewhere in the system another node that is the reference node, which we depict with this notation. Good. It is important to note that linear graphs can represent nonlinear system elements. The name is a reference to the lines used. So linear line Linear graph means it's just lines that we're drawing between nodes. Now, these lines could represent an element that has an elemental equation that's nonlinear. So, for instance, it could be a nonlinear resistor, and we'd have V equals R times like I squared. R would have to be in something besides ohms, but yeah. That is a potential elemental equation. So it doesn't have to be a linear relationship, even though we're going to use a linear graph. It doesn't mean that the system's linear. Although we'll mostly consider linear systems in this class because they're nicer to work with, and they get us a lot of the way there on a lot of analyses. So, all right, good. Yeah, so it is common to choose a node of the graph as the reference node. So choosing some node, and it's usually a completely arbitrary choice. Sometimes there are choices that are more physically meaningful than others. But you can technically choose any node to be the reference. And we use that node to be the reference for all across variables in that graph. Due to its similarity to the electronic ground, we often use these terms interchangeably. So we might call it the reference node, we might call it the ground. Either one is fine. So this is the reference node that's drawn here. We might call it the ground. Sometimes we might call it the reference node. It's fine either way. Okay, figure 2.3 shows how a linear graph can be constructed for a simple RC circuit. So here's our good old buddy, the RC circuit. And we're going to say, okay, we can come up with a representation in linear graph form. And there's a lot of things that are the same. So like, for instance, you take this resistor and you draw it as a branch, right? Boom. Notice that there are these arrows, and we haven't talked about what they mean, but it's going to be essentially the sign convention. And I drew it to be in the same direction as the current flow assumed sound direction, which is going to be, we haven't defined it to be that yet, but that's what it's going to be. So it's going to be the direction of assumed current flow. And so that's our resistor. Here's our capacitor. Once again, there's another element. It just looks, you just like chopped it out of there, and you represented it as a branch. The source, it's conventional to write to draw a source with a circle around the arrow, but technically you don't have to. It's just, I think, more comfortable to us because it looks more like the sources and circuit elements. So we usually do, we draw a circle around it, and we draw the arrow in the direction of the cross variable drop, in this case voltage drop. So plus to minus goes towards ground, so we draw it towards ground. And finally, the one thing that's actually kind of different is the node thing. So wires collapse to nodes. Okay, so remember we would refer to everything along a wire as a node, but we're actually now drawing that whole thing as just a dot. So all of that collapsed into this. All of this between the resistor and the capacitor collapses to this node. And then all of this ground node here collapses to a single point where or it doesn't have to be a single point. Anywhere along this ground where we draw this hatching on it is ground node. Occasionally we'll have a large circuit where we'll draw or a large system with a lot of elements, and the ground node gets referenced a lot, so we have to draw a lot of elements to it. So sometimes we'll draw longer, and we'll draw this graph like this.
How can you mark something as parallel?
So if things were parallel, they would be like this. So like if there was like an L here, it'd be parallel. That's why we use the curvy lines. because otherwise you can't use straight lines between nodes if you have more than one, because they'd be on top of each other. So you got to use curvy lines. And if you wanted another one in parallel, you just bloop, bloop, etc. Yeah, the sound effect helps too. So that's what we're gonna do. I mean, so it's easiest for circuits. It's like really similar for circuits, but for other systems, it's a little less intuitive. But we're gonna get some practice with that. All right, that's all I have for you today.